Hi, in this screencast I'd like to go over what we did in the last class about how to compute cohomology using the Mayer-Vietoris sequence, and I wanted to do a couple more examples. Okay, so let's start off with the first example which I did, which was the circle. Okay, so for the circle we're going to use two open sets, U0 and U1. Okay. And we know that each of these is homeomorphic to R. And we know that the intersection is two disjoint copies of R. Right, let me just draw a picture. So here's S1, and here's U0, here's U1, and the intersection of these two things would be two pieces, U0 intersect U1. So that's why I wrote this. The good thing about this cover is that we know the cohomology of each of these open sets by the Poincaré lemma, and we also know the cohomology of this by the same Poincaré lemma. So everything is very simple. So when we have to work out the cohomology of S1, we're going to, we always write it first. So we start off with H0 S1, and then H1 of S1. And we know that there's not going to be any H2 of S1 because S1 is a one-dimensional manifold, and so it only has 0 forms and 1 forms. And the way the Mayer-Vietoris works is that the first map is the restriction map to the cohomology of the disjoint union of these two open sets. Let me just make sure that it's clear that it's disjoint union. Okay, and this, okay, then when we have the two functions, one function here, one function there, we need to know the next map in the Mayer-Vietoris is the testing map. It tests whether the pair of functions actually agrees on the overlap. So this is the difference map, which maps to the cohomology of the intersection. So this goes to U0 intersect U1. And then this arrow continues to the next stage. Okay, so I'll just put a +1 here. That means go up one level and start at the left here. Normally I would draw the arrow as a snake arrow going like this, but I just want to leave this space here for calculation. Okay, and then I have a map to H1 to U0 disjoint union U1, and then to H1 of U0 intersect U1, and so on. But I know that the next thing is 0, so I might as well just put a 0 here. And I also know that this thing starts with a 0, meaning that this map here is injective. Okay? Remember that. Yeah, okay, so I think that's clear. So the statement of the Mayer-Vietoris sequence, what the Mayer-Vietoris proposition or theorem, is basically saying that because of the fact that we had a short exact sequence for the Durham complexes of these three spaces, S1, U0 disjoint U1, and U0 intersect U1, the Durham complexes for these three spaces form a short exact sequence. And as a result, the Mayer-Vietoris sequence is a long exact sequence, which means that at every position, we have that the kernel of the map out is equal exactly to the image of the map in to that position. Okay, and so what this means by putting a 0, remember, putting a 0 means that this map is injective, and putting this 0 means that this map is surjective. Okay, so let's just start filling in the information that we know. So the thing is that whenever you have whenever you have the cohomology HK of a disjoint union, X disjoint Y, you're looking at the Durham complex of a disjoint union, and those are totally independent. The Durham complex of X and that of Y they're totally independent, and so this is always the direct sum of X, direct sum with the cohomology of Y. Okay, and so here I know that H0 of this disjoint union is H0 of each piece, and I also know that H0 is just measuring locally constant functions, or functions which are constant on every connected component. But U0 is one component, so this is going to be R for U0, direct sum R for U1. Similarly here, S1 has only one connected component, so this is R. And this intersection has two connected components, and so this will be R direct sum R. Okay, and this map here is taking a constant function on S1 and restricting it to it's just restricting it to a constant function on U0 and a constant function on U1. And so that means that the generator 1 would be sent to just 1, which is the restriction of this constant function to U0, and 1, which is its restriction to U1. So we see that we have this injection of a rank 1 vector space into a rank 2 vector space. Let me just get rid of this. So this is a linear map from a 1 to a 2, and so that would be given by a 2-by-1 matrix, which is just the column matrix 1, 1. Okay, this map, okay, is the difference map. So it's taking a function on U0 and a function on U1, and it's taking the difference of those two functions and restricting to the double overlap. So, for example, the generator 1, 0, namely the function which is 1 on U0 and 0 on U1. Yeah, so here, let me just write what this map is as a 2-by-2 matrix. This is a linear map from R plus R to R plus R. The question is, where do the two basis elements go? Well, the first basis element is just a function which is 1 on U0 and 0 on U1. And that, if I take the difference of the values on the overlap, on this overlap region, I will get 1, and on this overlap region, I'll also get 1. So that means that the first basis element would be sent to 1, 1. On the other hand, the second basis element, which is, so here are the first basis element was equal to 1 on this factor and 0 on this factor. And we saw that the restriction and the difference 1 minus 0 on these two regions would be 1 and 1. Whereas if I take 0 on this open set and 1 on this open set, then 0 minus 1 would be minus 1 and minus 1 on these two pieces. And so the entries of this matrix would be this. Okay, and so you can see that we get a 2-by-2 matrix, but this matrix, you can see just by looking at it that it has rank 1. The determinant is 0, but it's not the 0 matrix, so it has rank 1. Okay, so this means that this map here is not injective. It has a kernel. That's no surprise, because Mayer-Vietoris says that it must have a kernel because the image here is one-dimensional. And indeed, this 1, 1 is in the kernel, right? If I multiply by the column matrix 1, 1, then I see that this vector is in the kernel of this matrix. But it's also telling me that the image has only dimension 1, which means that the kernel of this map only has dimension 1. So the fact that we've computed this matrix, this implies that, let me call this map delta. It tells us that the kernel of delta has rank 1. And this implies that its image, okay, the image of delta must have rank, just because this is two-dimensional, right? So if it has a one-dimensional kernel, its image has to be with dimension 1. Has dimension 1. Sorry, here, kernel delta has dimension 1. That's what I meant to say. Okay, and if the image has dimension 1, then, well, okay, so then we know that this space here has at least dimension 1, but it may have higher dimension in principle. But in order to figure that out, we need to look at this step. So at this step, we see that this is h1 of u0, but u0 is isomorphic to R. And we know by the Poincare lemma that this, so the Poincare lemma tells us that this has no cohomology except in degree 0. So that means that this whole thing must be 0. And similarly here, this must be 0. But anyway, the point is just that this implies that delta is surjective, because this h1s1, what's happening right after it is a 0. So that means that this map delta must be surjective. So I would say, but the Poincare lemma implies that h1 of u0 is equal to h1 of u1 is equal to 0, which tells me that delta must be surjective, which means that the dimension of h1s1 must be equal to 1. Okay, so this tells me that the cohomology of s1 is in degree 0, it's R, and in degree 1, it's R. Okay. And I'd also like to point out that this is actually a ring. Okay, because remember that these cohomology classes, they are represented by differential forms, and the differential forms form a ring, and that ring structure descends to cohomology. So just to see what happens to a basis, let's figure out the ring structure. So if I take an element, let me call this element E0, an element in here, and an element, a basis element E1. So suppose we choose a basis. Okay, then we know that yeah. So the point is just that these are forms. So this is a 0. Better to write it this way. Okay, suppose we choose a basis. For h0 of s1, and another basis for h1 of s1. So we know that a basis element is a cohomology class, and it is represented by this differential 0 form. A differential 0 form is just a function, and the function has to be constant because it's a closed function. So this is a closed form and this is a closed form. So actually we could just take rho 0 to be the constant function 1 on the circle. The constant function on S1. And then rho 1 is some closed 1 form. Notice that all 1 forms on the circle are closed because D of rho 1, that would have to be in the 2 forms, but there are no 2 forms on S1. This is just 0. So anyway, right, so now I have 2 generators for the cohomology, And if I want to figure out the ring structure, well, all I have to do is take, let me do it down here. Let's move this down. So if I take row 0, wedge row 0, this is just the product of functions, so it's just 1 times 1, so it's just row 0. And if I take row 0, yeah, so if I take row 0, wedge row 1, I just get 1 times row 1, which is row 1. And if I take row 1, wedge row 1, this must be 0 because I'm taking the wedge product of two 1 forms, and there are no 2 forms. So this has to be a 2 form, but there are no 2 forms in 0. Incidentally, if I took any 1 form on any manifold, then it's automatic that mu wedge mu must be 0, because mu wedge mu, right, must be equal to minus mu wedge mu, because if I flip mu and mu, well, let me write it like this. Mu1 wedge mu2, if these are 1 forms, let's say mu1 and mu2 are both 1 forms, then mu1 wedge mu2 must be equal to minus mu2 wedge mu1. And this is true for any 1 form. So in particular for mu1 equals to mu2 equals to mu, so this just tells me that mu wedge mu must be equal to minus mu wedge mu, which means that it must be equal to 0. So anyway, that's just a digression, just to give you some feeling for the 1 forms. So this is giving us the full ring structure now, and I can write this ring structure in a different way. I could write it this way. I could say that it's R, join a generator. Let me call it E, where this generator is E. Okay, and I know that E squares to 0. Okay, so this is just R direct sum R times E, and so it's like the polynomial ring in one variable, where the square of the variable, that ideal, has been, you mod out by that ideal, and you get this this ring. This is it's a very simple two-dimensional ring. It occurs a lot in algebraic geometry, and it's called the ring associated to the fat point. But anyway, I'll leave it at that. Okay, let's go to the next example. So maybe just to go over this one more time, the Mayer-Vietoris sequence in this case, right, it looks like this. Okay, it's really a 4-term sequence, the Mayer-Vietoris sequence, for the case of the circle. And we know that this is an R2 and this is an R2. And what we have is a rank 1 linear map in the middle. And this tells us, the fact that we know this map tells us right away what the kernel is, which is 1-dimensional. And it also tells us what the co-kernel, this is sometimes called the co-kernel of this map, of this matrix. The co-kernel is the codomain mod the image. So the codomain, the domain is R2, the domain contains the kernel, the codomain is R2, and it contains the image. And the quotient of the codomain by the image is this space, which is sometimes called the co-kernel. Okay. So anyway, this is a famous type of scenario where you have just a 4-term sequence, and the middle two are related by a linear map. And so everything is determined by the structure of this linear map. Okay, next example. So let's say that we do S2. Again, we're going to express it as the union. And union of U0 and U1, where U0 and U1 are equivalent to R2, and U0 intersect U1 is homotopic to S1, because it's like the equator of the two-sphere. Okay, so that's very important. That you see, this is a two-dimensional open set inside S2. It's a two-dimensional manifold, and we have this intersection. And all I'm saying is that the intersection looks kind of like a band, an equatorial band, which goes from a certain latitude to another latitude. And anyway, it's homotopic to the equator, which is an S1. And this, incidentally, is homotopic to a point. Okay, so that means that we know the cohomology of all of the spaces involved. Okay, so that should be, now we should be able to go to town. So we start with H0, S2, H0 point, disjoint union point, because the U1 and U0 and U1 are homotopic to a point, and the cohomology doesn't depend on homotopy. It's a homotopy invariant. So, and this goes to H0 of the intersection, which is S1, and this continues with delta to the next step, which is H1, S2, H1 point, disjoint union point, okay, H1 of S1, and then there's a delta again, which again is +1, up to the next level, which is H2, S2, and H2 point, disjoint union point, and H2 of S1, and so on. Okay, but right away we're beyond the dimension of S1, so this will go to 0, and this goes to 0 as well, because we're beyond the dimension of the point. Similarly here, this is 0, and then we need to analyze all the rest. So we from our previous calculation, we know what this is, but we need to determine these three spaces. This is what we're really interested in, is these three spaces. Okay. Okay, so the first thing I want to point out is that this space here is sandwiched between zeros. And whenever you see a sequence where one of these things, one of these groups, one of these vector spaces is sandwiched between two zeros, it must be 0. Why is that? Well, because the kernel of this map is everything, because this is the 0 map. But this kernel must be equal to this image, which is 0 as well. So the image and the kernel must be equal. The kernel is everything, the image is 0, so that means that everything must be 0. So this whole space must be 0. So this is the case of sandwiched between 0. Okay. So this determines this space as being 0. Okay. And the next thing, I'll just take a look at this. So H2 is not sandwiched between zeros, but it's occurring in a part of the sequence, which I'll reproduce here. It's a sequence that begins with 0, and then H1, S1, and then delta, and then H2, S2, and 0. And here we see that we have zeros on either side, and then just a single map. Well, the kernel must be 0, and the image must be everything. That means delta must be injective, and surjective, which means that delta is an iso. Okay, so whenever you see zeros and a map between two spaces with zeros on either end, it implies that this must be an isomorphism. And so by induction, well, because we already computed H1S1 to be R, this implies that H2S2 is also R. It's a one-dimensional vector space. So this determines this one. And then, of course, H0 of S2, we could determine it immediately because S2 has only one connected component, and so this is R. So this tells us that, or you could look at the kernel of this map and see that it's one-dimensional. So this means that the cohomology of S2 is, in degree 0, it's R, in degree 1, it's 0, and in degree 2, it's R. So this is the first space that we see a second-degree cohomology class. Okay, and this second-degree cohomology class, it is represented by a form, a differential 2 form, and that differential 2 form, you could take it to be a volume form on the 2-sphere. So this here is how we would be able to detect the volume of the 2-sphere. Anyway, we'll discuss that when we discuss the integration of 2 forms. So, but in any case, this is also a ring, and we could, it's just an exercise to check that this ring is isomorphic to the previous ring. In fact, the cohomology, you should think of it not just as a ring, but as a graded ring. And so, just as rings, this is the same as the cohomology of S1, but as graded rings, it's slightly different because this generator is in degree 2 rather than before it's in degree 1. Okay, now in general, for, let's say, as a third example, which you should work out in great detail on your own, let's just think for a moment about the cohomology of Sn. Okay, so in the case of Sn is always going to be, we can always represent it as the union of 2 open sets, where each of these is homotopic to a point, and U0 intersect U1 is homotopic to the previous sphere, Sn-1. Okay, and as a result, if we were to write this type of a sequence, it would have n plus 1 rows going all the way up from H0 up to Hn. Okay, but if you notice that this column would continue to be just points, right? And this column would be the cohomology of the previous sphere. Okay, so so this means that that if we start, let's say, at H0, so if we start, let's say, at H0 of, let me just do the next sphere just to give you an idea. If you start at H0 of S3, we know that this is going to be R because the sphere is always connected. The next level would be H1 of S3, and then we'd have H2 of S3, and then H3 of S3. Okay, and here we would have points, so this would mean that here we'll have R plus R, as before, and then above that would be H1 of a bunch of points, and so this is just zeros. And then here I would have the cohomology of the 2-sphere. Okay, and so what we see is that because this is 0, this is R, and this is R, from the previous calculation here, what you see is that going up, we have, well, there's a couple of different things that are happening. So, for example, here, we see that we have a sequence 0, 0, H2S3, 0. So this means that H2S3 is sandwiched between zeros. So this tells me that that's 0. And similarly, I see that I have 0, this part of the sequence, 0 maps to H2S2, which is R. Delta maps it up to H3, and then it maps to 0. So I have a similar situation as up above, where I have a single map, delta, and this map is sandwiched between zeros. And so this must be an isomorphism. So again, I get that H3S3 is isomorphic to H2S2. So the top cohomology of the 3-sphere is isomorphic to the top cohomology of the 2-sphere, which is isomorphic to R, and so on. So that deals with this and this. And then I should say that there's a simple argument for H1 of S3, and that is just that if we look at this map here, remember that this is the, the kernel of this map is the image of this map. This is an injection of a one-dimensional space into here. So that means that the kernel is only one-dimensional, and so the image is one-dimensional, and this is a one-dimensional space. So that means this is surjective. So the fact that this map is surjective means that rather than having this unknown delta map which maps up here, I can actually, this map here is surjective, which means that the kernel is everything. The kernel of delta is everything. That means delta must be the 0 map. So one way of emphasizing that is to just break the sequence and put zeros here and here. Okay. That's equivalent to having a single map from here all the way up here, which the map itself is 0, right? I mean, here, there's no difference here. So what this means is that because of the fact that this map is surjective, okay, delta, the connecting homomorphism, must be 0, and as a result of that, H1 is sandwiched between zeros, and so I get that H1 is 0 as well. So in the end, for S3, I'll just get R, 0, 0, R. In rank, in degree 0, 1, 2, and 3, the cohomology of S3 is like this. So in general, you can see for yourself, using these sandwiching arguments, that the cohomology of the n-sphere is R in degree 0, 0 in every intermediate degree, all the way to n minus 1, oops. And then in degree n, I have R again. So it's only two-dimensional, one-dimensional in degree 0 and one-dimensional in degree n. Okay, so let's continue with another example. So I'll do one other example, which is R2 minus 2 points. Where P is not equal to Q. So here's a picture of R2, and I have 2 points which are removed. Okay, so I need to choose some open sets. So one open set will be like this. I can just choose it however I wish, but let me call that U. And another open set V, like that. So I'll write this space as, let me call it M, M is U union V. Okay. I chose these open sets because I know that U is homotopic to S1. Okay, because U is basically a plane, a half plane, okay, which is contractible, but actually it's not a half plane because I have a point that's absent from, it's removed, P is removed. So this is actually a punctured plane, and a punctured plane is homotopic to the circle. So U is homotopic to S1, and so is V, and U intersect V is homotopic to a point. So again, I know the topology, or the homology, the cohomology of all the spaces involved. Okay, and so as a result of that, I can just do the Mayer-Vietoris sequence. Okay, so let's look at the 0th level. So the 0th level is going to go to H0 S1 plus H0 S1. So that's going to be R plus R. And then the intersection is contractible, so it'll have H0 equal to R. And again, this part of the sequence, this map, M is connected, so this is R. And this is surjective, so this actually splits off of the rest of the sequence. So, so this means that I really only need to consider starting with H1 of M. Okay, H1 of U and H1 of V are both R, because we know that the first cohomology of the circle is R. And then H1 of the intersection is 0. Then we have the connecting homomorphism, which goes to H2 of M, and H2 of the circle is 0. So what I see is that H2 is sandwiched between zeros, so H2 is 0. Let me just write this a bit nicer. So if I look at the cohomology of M, in degree 0 it's R, because this is a connected space. H1 is, so we have H1 mapping to R plus R, mapping to 0, and if we look to the left of H1, it's 0. So that means that this map is sandwiched between 0, and therefore it must be an isomorphism. So this must be R2. The first cohomology must be R2. And then the second cohomology is sandwiched between zeros, so it's 0. Okay, so this is the cohomology of R2 minus 2 points. So you can use this type of technique to complete the assignment where I asked about various subsets of R3. Another interesting example would be the genus G surface. Actually, we could even just start with the torus. Right? And you could try to use an open cover of the torus. I would recommend that what you try to do is try to use the Mayer-Vietoris sequence in on the same space, but using different open covers, just as a kind of experiment. So you could, for example, try to decompose this into one of the open sets could be this, say, this half of the torus, and the other open set could be something like this, say. The other half. Okay, so you would have a situation where U and V, so you would have a situation where U is homotopic to the circle, V is homotopic to the circle, because you could just squish this whole thing just by sliding this circle along here all the way down to this circle, and we just get that U is homotopic to the circle, and V is also homotopic to the circle, and then U intersect V is homotopic to the circle. oops, excuse me, U intersect V is a disjoint union of two circles. Okay, so if we wanted to compute this, it's a little bit trickier example, but we could, so let's just begin with the first row, H0. We know that H0 is R. H1 of U plus H1 of V, that's going to be an R2. The intersection has two connected components, so that's also an R2. Notice that this is different from previous examples. We'll have delta, which is going up to H1. H1 of the whole space. I'm just not writing the I could write it in here else, but let me not write. So this is the first column, of course, is the cohomology of the space in question. Then I'm going to have H1 of U plus H1 of V, which is another R2, because each of U of V is the circle. And then the intersection is two disjoint copies of the circle, so I'll get an R2 again. And I'll have delta up to H2. And then that will go to 0. So now we see that here we've seen this type of map before. It's taking a function on U and on V, so it's a function on the disjoint union of U and V, constant functions. It's taking the difference of its values on U and V and restricting it to the intersection. So for example, if I had the function on U and V, if I had the function 1, 0, then the difference would produce on each component, it would produce just 1. And if it was 0 and 1, then it would produce -1, -1. So again, we have this matrix which looks like just 1, 1, -1, -1. So it's a rank 1 matrix. The fact that this is a rank 1 matrix means that the image has dimension 1, and therefore the kernel of delta is one-dimensional. If the kernel of delta is one-dimensional, that means that the image is one-dimensional. So, so what we could do is to just simplify this sequence, what we could say is that delta is actually surjective onto a one-dimensional space. And that one-dimensional space injects into H1. This is just a way of splitting off the first row from the second row. So in other words, all I'm saying here is that there is a one-dimensional space that's injecting into H1. What is that one-dimensional space? It is the image of delta coming from H0 of the intersection. Okay, so this means that we've split off this sequence, and now we have to deal with this sequence. Okay, now the same type of calculation is going to happen here. I have a 1 form on U and a 1 form on V. I have to take the difference between them and restrict to these two open sets. And with some thought, you can see that the same exact phenomenon will occur, that this is also 1, 1, -1, -1. And so this is also a rank 1 map. Again, the fact that this is a rank 1 map means that we could just say that whatever the image is, it's some one-dimensional space which injects into H2. And then we have our simplified sequence. Okay, so this is telling us, this part here is telling us that H2 is one-dimensional. So far we know that the cohomology of T2 is R in dimension 0 and R in dimension 2. And we just need to know what it is in dimension 1. Now in dimension 1, we see that there's an R mapping into it, and we see that that it is mapping to this part of the sequence. But remember that this map here has rank 1. It has a one-dimensional kernel. The kernel here is the image of this map. So this means that that H1, there's a map from H1 here. So let's just zoom in here to a part. So let's just take a look at what's happening here. So H1 has a map to R2. Okay, and this R2 has a, if we look at the kernel of this map, it's a one-dimensional subspace in R2, and that kernel is the image of this map. So I could forget about this full R2 and just look at that one-dimensional kernel, okay, and just simplify this sequence a little bit by replacing R2 by the kernel of the successive map. So this is telling us that this sequence is informing us that H1 has a map to a one-dimensional space, a surjective map to a one-dimensional space, namely the kernel of this map. And the kernel of that map is the image of this map, which is an injection from R. So this is telling us that the dimension of H1 must be 2. This must be a copy of R2. Okay? Because it has a map to R, which is surjective, with a one-dimensional kernel. Okay? So this is telling us that this is R2. Yeah, and actually this is an instance, for those that are interested, this is an instance of Kuhneth theorem. Okay, Kuhneth theorem is not part of the course. Kuhneth theorem says that if you want to compute the cohomology of a product, all you need to do is put the cohomologies. Let's say if I'm taking, let's say, S1 cross S1, the cohomology of S1 cross S1, okay, the way that you figure it out is that you put the cohomology of S1 down here, namely 1, 1, and you put the cohomology of the other factor, S1, here, and then you just take the tensor product of these spaces. So this is like R tensor R is R tensor R is R tensor R is R tensor R is R, and then what you do is you take the diagonal here, so you end up with H0 is this diagonal, so it's just R. H1 is this diagonal, so it's R direct sum R. And H2 is this diagonal, so it's just R. In fact, and that's indeed what we found. That's the cohomology of T2, which is S1 cross S1. On the other hand, if you wanted to compute, let's say, the cohomology of S1 cross S2, what I would do is put S1 here, S2 here, take the tensor products, and then take the diagonal. The first diagonal would be 1, the second diagonal would be 1, the third diagonal would be 1, and the fourth diagonal would be 1. And so indeed, this cohomology is just R, 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 and R. Okay, I'll leave it at that. You should try to cook up some examples for yourself and try to use different open sets and figure out what the maps in the Mayer-Vietoris sequence actually are. Okay,